Hello, everyone. Thank you for this opportunity to speak and putting on this conference. I am Ben Kaiser, a PhD student at the University of North Carolina. I will be discussing the detection of lithium in cool white dwarf atmospheres and what it implies about extrasolar planetesimals in the context of the work I completed under the 2020 NC Space Grant Graduate Research Fellowship. When stars like the Sun finish burning their nuclear fuel, they shed their outer layers and leave behind a dense core called a white dwarf. Planets and asteroids are still orbiting the stellar corpse, and sometimes they are thrown in toward the white dwarf. The white dwarf's incredibly strong gravity rips the planetesimal apart. These chunks are ground down to progressively smaller sizes and spiral inward, eventually onto the white dwarf, where we can then measure the planetesimal's elemental abundances using spectroscopy. I was recently lead author on a paper that identified lithium and potassium for the first time in exoplanetary material accreted by a white dwarf, the spectrum of which is shown here. The central goal of my NC Space Grant Graduate Research Fellowship was to try to find these elements in the exoplanetary material accreted by another white dwarf to increase our sample size. We identified a tentative lithium absorption feature in the archival Sloan Digital Sky Survey spectrum of white dwarf SDSS-J 1636 plus 1619, but follow-up was required to confirm the marginal signal. To that end, I was the PI on a director's discretionary time proposal to observe J 1636 using the Gemini North GMOS spectrograph. The locations of absorption features in the spectrum are marked. However, we did not detect any of these absorption features, so that's where we were looking for them. They weren't there, apparently. So my collaborators were only able to establish upper limits for the abundances of these elements in J 1636. Our goal to increase the sample size of lithium detections was partially accomplished, however, thanks to another research group publishing 3 additional white dwarfs with lithium detections shortly after our own paper was published before. Here we plot the lithium to calcium ratio versus the sodium to calcium ratio of the 5 accreted planetesimals with lithium measurements and our limit for J 1636. We can see that for those objects for which we have lithium detections, the lithium abundances are on the higher side of rocky bodies of the solar system, and one of them, J 2317, is very far from the rocky bodies of the solar system. It's worth considering why this could occur. One thing to think about is lithium was in fact made in the Big Bang, while the other metals, such as calcium and iron, had to be formed in stars or other processes over time. Therefore, the lithium to iron ratio was high in the oldest nebulae that formed planetesimals, and then subsequent generations of planetesimals would have formed in nebulae with decreasing lithium to iron ratios. You can see our solar system lithium to iron ratio down here is the blue square. The lithium overabundances of the previous slide are most likely at least partially the result of the greater abundance of lithium relative to iron and other elements originating from the nebula. Because we know these white dwarfs are relatively old from age dating of them based on cooling ages and main sequence lifetimes. And so if we account for the slight age mismatch between Prantos 2012's predicted lithium to iron evolution, which assumed a 12 gig year disk, if we instead assume a 10 gigayear-old disk, which is consistent with numerous recent measurements in the literature, 10 gigayear-old disk, we end up with this dashed line approximately. This is an approximation I made for the other one. Yeah, we end up with this dashed line, which tracks, generally speaking, the abundances of the planetesimals accreted by our white dwarfs. J1824 is not included in this plot because it doesn't have an age available. We can also see that J1636, the pink point, falls slightly below the main cluster of lithium abundances. This is likely the result of a geological alteration of the lithium abundance in J1636's planetesimals formation. All of the other ones are probably relatively accurate, direct representations of their nebular abundances. So we know that there can be slight geological alteration. So the marginally lower value is most likely a geological alteration, as was shown with solar system bodies being capable of having lowered lithium abundances previously. Thank you for your time.